Okay, this is an example of the kind of things that we can do with SFEPY. And the basic idea here is that we want to solve, sorry, a linear elasticity problem that is described by the equation that you see here. So basically, this is the equilibrium equation where you have stresses, and this is the body forces. F is the body forces, which can be gravity or some other force applied to the material. And then you have some domain where you are solving the problem. It can be a piece of rock or something in the subsurface, and then some boundary conditions. U here is the displacements, and it's a vector because you can have displacements in 3 different directions. And you need to specify boundary conditions. For finite element, you need at least 2 points for solid mechanics. Here, and I'm going to show you what these boundary conditions mean in a moment. And then there is some complexity familiar with linear elasticity. This is familiar to you, but probably you are not. So but this is a constitutive equation. So the stress field is related to the strain, which is epsilon here, following this what is called a constitutive equation, which is linear elasticity. Lambda and mu are known as Lamé constants, and the strain is defined by this equation here. Probably can expand this a little bit more. It doesn't have much with equations, right? F are the body forces, and then you can actually express the. You can relate the stress to the strain by following this equation where D is the linear elasticity constant, or linear elasticity tensor, I should say, that can be related to the Lamé constants by this equation. So there are only 2 independent constants, but there are like, you know, I don't remember how many terms on this equation, but it's a lot of terms. You see, it's a 4-rank tensor. And this is the simplest problem you can solve really with linear elasticity with only 2 constants. So in order to apply finite elements, you need to express the equations in what is called the weak form. And this involves some mathematical transformations that there is an error here. Okay, I'll fix this later. That requires the definition of a test function, what is called a test function or a test variable, where U, in this case, is the actual physical displacements. V is actually a mathematical artifact that is used for the finite element formulation. So the first thing that we do is from SFEPY, we import some of the functions. In particular, we first need to be able to define a mesh. I'll show you. I'll go back and forth, and then you will see what each one of these things mean. You need to create a domain and define the fields that you're going to be solving for. I have a mesh that actually they provide when you clone the repository. They will give you some files, but also SFEPY has the ability to create and modify existing meshes. Meshing or gridding is a big subject in finite elements. So most likely we will be talking about that in one particular session because it's a very complex subject. But for in most cases, you use an external package in order to create these meshes, and then you just use them. But this package, the idea of SFEPY is that you can start with a mesh and then you can modify it. That's what I usually do. So once I have a mesh, you need to create a domain, and that domain you use this function that we imported here, and basically the idea is to provide a name. It's useful to give names to the different objects, because then you can refer to them by the name, and rather than the variable name. So we define the domain. And the nice thing about this package is that it will give you the ability to understand the geometry that you're working with. And in this particular case, we can extract the bounding box. So, and then we can extract the minimum and maximum x. You will see in a moment when I visualize the problem what I'm talking about. Well, in fact, if I can tell you now. If you see this, this point here, we are solving a problem like this, a rectangle, and then we're applying some boundary conditions to see how the deformations happen. So this will be min x, whatever that number is, and then this max x. And the reason for extracting this is because I want to apply boundary conditions there, so I want to know those coordinates. So sometimes I don't know the numbers exactly, so I need to have functions that allow me to interrogate the mesh or the domain in this case, right, which is related to the mesh. And now I create this error, which is 10 to the minus 8 at different. Now we can create a domain, different regions, and the regions are for different purposes. And this is what SFPY allows us to create domains in multiple different ways. So for example, omega will be the domain where I'm solving the equations. I create the region, call it, give a name, and say how I am selecting that domain. In this case, it's all. That means that it's a full mesh, right? I'm going to be solving the equation in the full mesh. And then I have gamma 1 and gamma 2, which are, as you saw here, places when I want to specify boundary conditions. And this is the way that, one of the many ways that it can be selected using this package. So I give a name, and then I say vertices, which means that are, I'll show you in a moment what the vertex is. So I'll show that in a moment. And then basically the idea is to select the min x plus an error. So which means that what I'm selecting by using this equation is this face. So whatever segments on the face such that the min x plus a small number such that the x, the coordinate x, is less than the minimum x plus some number, some small number, which means this is going to select all the elements on the mesh that are on this line. And the same happens. The same for gamma 2 is going to be the elements that are on or close to the right side of the box. And I say what type of domain this is. This is optional. This is a face, basically. So those are three regions. I think I can visualize those already. Let me make sure I have executed this. Let me go at some point here. Oh no, I cannot visualize for. Okay, I'll do it in a moment. So now we need to define an approximation. So basically, a finite element method requires the specification of an approximation. So I define a field, give a name to that field, and this is basically to tell the package what kind of approximation I want, what kind of number I'm using, and what kind of variable I'm working with, and this is a vector. This is the domain I created before, and this is the order of and this is order 2.
Adolfo, excuse me,
yes.
What is NM there?
Oh yeah, NM, this is a NumPy actually. So for some reason, this guy who wrote this package likes to use NM for NumPy, but that's equivalent. I think the reason, and this is one of the problems when you import packages, giving an alias, right? Is that sometimes you may be using NP for something else, and I think that's why he decided, the guy who wrote this package decided to use NM most of the time, because I think he uses NP for something else. But NP is the most conventional way to name NumPy. So hopefully I'm not gonna mess anything with this example. But yeah, good question. Yeah, I forgot to mention that. Now there are a number of things that we need from the package, from SFEPY discrete. We need the ability to fill variables, materials, integral functions, equations, and the problem, and how to define a problem, right? So what happens in finite elements is that you typically have one set of unknowns, one or multiple unknowns. And for each unknown, you have a test variable, which is need to correspond. You need to be able to define that test variable and say to which variable it matches. So in this case, U is an unknown. It's something I'm going to be solving for, and it's defined over the field, which I defined before. Somewhere. Oh, here. The field was defined here with approximation and everything. And the second is going to be a test function. It's defined over the same field, and the corresponding primary variable is U. So this is the way we do this using finite elements. So if you had more variables, you need to define those variables plus the corresponding test variables. So, and then we need to define the material properties. And then you remember in my formulation here, I have the Lamé constants, which are this mu and lambda. Delta, by the way, is the Kronecker delta. So whenever I is equal to k here, this is going to be 1 if that difference is 0. So with this, you end up getting a tensor of this order. So linear elasticity is a little bit complex in terms of the mathematical formulation, but if you don't, if you trust that these are the questions that you are solving, you don't need to get too deep into how these equations work. And this is the message I want to pass. So this is a problem that may be very, very difficult to formulate, but once you know this formulation and trust the formulation, you can go and solve the problem using this package by following this approach. Of course, there are the complexity that you can handle using this package is basically has no limits. So you can solve equations as complex as you can imagine, and I'll show you a little bit of that. So the idea here is that if you learn how to install it, you install and then solve some problems. You can use the examples and this example that I'm going to provide, visualize, and then you can start being a little bit more creative about how to solve other problems that you may have. So now we define the material properties. in this case, we want to define D, actually, the stiffness, and there is this nice function, stiffness from Lamé. You see that you give the dimensions and the properties, and then this is going to take care of the transformations, which is, if you go back to the beginning, this is the transformation we are talking about. And of course, if you had to do this, you would have to compute this, but now we have that function, it takes care of that transformation. Again, you just provide two variables, two Lamé constants and a dimension, and this is going to take care of computing that. And then we have the body function, which is or the body forces, I should say, which is something like gravity, for example. In this case, we have x and y because it's a vector. So this is the way we provide it. And in the original example, they had something like this, which is probably difficult to understand what those could mean. But if you just provide one number, you can imagine that this is the gravity, something related to the gravity somehow. So and it will be gravity times density. So no problem there. So you would have a body force, and I'm gonna show you what happens if you change that value, how this is going to change the results. So whenever we do finite elements, as you saw, the weak function requires integration. So we need to provide the order of that integration, because this is going to be a numerical integral. So numerical integrals can be done at different approximation orders if you have done that numerically. So we say it's order 3. It can be something else, but the higher the order, the better the approximation. And then you also provide the name. And now the fun part is how to define the equations. Once you have your domain, your mesh, boundary conditions. Well, actually, we haven't defined boundary conditions. It comes next, but we have defined the boundaries, the domain and the boundaries. Now we can define terms, and this is something that they provide. They provide terms and different kind of terms in the package. And I'm gonna show you because it is amazing what they do here. So this is a table of basic terms, and then you can use all these terms or any combination of these terms to solve the equation that you are looking at. So you already have formulated your problem, and now you are ready to solve it, right? And it may be a simple problem like I'm showing right now, simple in the sense that it's just one kind of physics that is very well established, and then you know the term that you are looking for. In this case, you see linear elasticity. Or you may have something more complex, and then once you have formulated your problem, you need to come here and see how what your term looks like. And as you can see, there are all kinds of physics, so you can solve any kind of physics. This is the one that we are using. This one, linear elasticity, and you see this is the term, right? And when you look at the formulation here, this is the term we are looking at, right? Which is linear elasticity term. And then we go here, let's see, and the other term is there somewhere. But this is, the beauty of this is that you can apply this to solve almost any kind of physical problem that you may be, you may need to solve. So this is something that, well, the reason why I think it's important to know these packages is because, yes, somebody has a question.
Yeah, sorry, Adolfo.
Yes.
Is there some, hey, sorry for interrupting.
No, no problem, no problem, that's the idea.
I just want to know, is there some option for solving the Navier-Stokes equation?
Yes. Yeah,
Oh.
you can use this package to solve a Navier-Stokes equation. Yeah, let me find the term. I probably will have to do a search. Oh, that's it. That would be Stokes. Okay. Okay. Here's the Stokes term.
Okay.
So you will have to build it, right? You will not find exactly the Navier-Stokes. So you find the Stokes term, and then you find the pressure term, and so on and so forth. But yeah, you can solve Navier-Stokes, and then you can couple it to other things. Like if you have temperature or you have something else, you can also add it. So there are no limits, basically, for this.
I think I saw some option like a Navier, just Navier in the list, but I'm not sure. But I see.
I cannot find Navier, but the Navier-Stokes equation is a combination of multiple terms. So it may be that you don't have exact, but the Stokes term is one of them, right? So yeah. we can look at that. In fact, if you have a problem that you want to solve, probably we can talk about that, and for the next session we can concentrate on the problem. So my idea was to show geomechanics, but actually, as you can see, you can solve any problem that you want.
Yeah. Thank you very much, Albert.
Yeah, you're welcome. Something that is interesting is that there's so much physics involved in this field that actually you want to have the ability to solve any problem that you want. For example, if you have a reservoir simulator, you know that a reservoir simulator will just be useful for that. Now I lost my. I guess this is it. Yeah. But in this case, and also I have used this package for multiple papers. I think probably 3 that I can remember right now. And one of them was using this package coupled to a reservoir simulator. But that's a kind of advanced subject to do coupled flow geomechanics. Okay, now that we have the terms, and you can see you can add, of course, these terms have to make sense. They have to come from the physics formulation of a problem, so the mathematical formulation of a problem. Probably you can add terms here, random terms, and it may be that you don't get an actual solution. They may not have a solution, or you may not know what the solution means. So actually, the way to do it is you have you have physics, some physics that you want to solve. You do a mathematical formulation, and then you compute the weak form of equations. And now you can go to this table that I just showed and find equations, the terms that you need. You find the terms that you need. You have to define, the mesh, boundary conditions, so on and so forth. And now you can build your terms here. Your terms, you create the equation, one equation, right? And then you solve. You create a list of equations. That's the way this package works. So now we set the boundary conditions. What we're going to do is on gamma 1, and you remember we defined gamma 1 here, all the left phase of our problem is going to be fixed in all directions. And this is the way you do that. You say u.all, and this is 0. It could be a number, right? It could be something else. But this is the way we fix a boundary condition. We create the domain. We create a region. That region is good for debugging or something else, but we really don't do anything with that. And then we can, for the other side, we're going to create a function.
You had an omega before, no?
Yeah.
Is it the same, or you're overwriting?
That's a good point. Oh yeah, it's actually the same line. Is the same line?
Okay.
Yeah, I duplicated the line for some reason. I don't know why. Create region. Yeah, I don't know why I have this line here. Well, I was testing something. Here we can create a function, and this problem is interesting because you can specify a fixed boundary condition for all elements belonging to one region, but you can also define use a function, and the functions need to be to follow exactly this structure. So T is for time. This problem is static, but it may not be. So they always we always need to provide time. So even though it may not be used, course is the coordinates. So here we are using the first coordinate, which will be the y coordinate, right? And then we can provide additional parameters here. So shift is an additional parameter that can go here, and the default is 0. Right? We define this function, and then we create a boundary condition, a variable that contains that condition, and this is the way we specify it as a function. We give a name. Doesn't matter what name it is. So sometimes it can be found. This name doesn't have to be the same as this. This is just a string, right? So, and this is the actual name of the function. And these are the extra arguments. So you can have multiple arguments here. It doesn't have to be one. We can test that with multiple arguments if you want. And then we call that boundary condition. It's essential boundary condition because we are specifying the displacements. Essential boundary condition refers to the primary variable that we are solving. And this u.0, what it means is that it's the x direction. So this function is going to be it's going to be applied to the x direction of the boundary condition. This takes a little bit of getting used to, and look at multiple examples to create this boundary condition, but it's really not that complicated. So compared to solving this problem by writing your own code, for example, if you wanted to solve the Navier stop and you want to write your own code to do it, that would be really messy, really complicated. So we need linear and nonlinear solvers for this, and then we are going to be using the direct solver that comes with SFEPY. So we don't need to import it because SFEPY will import it for us. And then nonlinear, for the nonlinear solver, we just use Newton, and this is a really nice way to specify this. So and it's a really interesting way because you can experiment with different solvers, and I have done that, and at some point we can look at that. Then we are ready to define our problem. Our problem is called elasticity, and the equations are the ones that we defined before here. We only have one equation, but you have to create this list because you may have multiple, and then that's the way it's defined. So now we are ready to save our regions. This saving of the regions is just for visualization. So these regions have been created here. And now we can save. Let me show you. I think. Let me continue with this flow because I may get confused. So now we can set the boundary conditions, and we have created a problem here, and I can set boundary conditions this way. Now I can set the nonlinear solver, and the nonlinear solver already contains a linear solver inside, so no need to specify that again. This is just for my status, and now I can solve the problem. So, and the problem is, once you have defined all that, it's just type PV times solve, right? And this status is for storing errors and other things that you may need to QC your problem to see if you actually converge and what kind of errors you have. So here I can show the nonlinear status, and then you see the time it took. It took only one step, because even though I'm doing a nonlinear solve, it's actually a linear problem, so it takes only one step to converge. And then let me show you now that once you have the solution, okay, what can I do with that solution? You can save it to BTK. But before, and then SFEPY contains the viewer as well, which is something really nice. Let me visualize the, oh, my kernel crashed. And that happens sometimes when I import the viewer. And I think I would need to execute everything again. For some reason, the kernel crashes when the viewer is imported. So what I'm gonna do now before importing the viewer is to show the solution using Paraview, so that I don't have the okay, save the states. And then let me go to Paraview. So Paraview is also an open source visualizer that can be used to visualize BTK and other kind of formats. So open region, let me show you the regions, because I didn't visualize them before. Okay, I can visualize, remember, the gamma 1, gamma 2, and omega regions. Let's say I want to visualize gamma 1, and that's my left side. The reason you see it this way is because these visualizers try to interpolate, but I can show you also the grid I'm using. So this was the grid I loaded from the files. And this is the boundary condition, or the region where I'm applying fixed boundary condition. I can look at gamma 2, this is the other side. And of course, omega is the full domain. Now let me open the solution. Let's close that one and open this one. And then I can look at U, which is my variable. And this is what I got. I can see X direction. And you see the scale here. It tells you that red is positive, which means that these points in the X direction are moving in that direction. And blue is negative, so basically you have something like that, some kind of curvature. Hopefully, the visualizer is going to work, and it's going to be much nicer to look at that. I can show the grid here too. So this is the solution of the problem on Paraview. Now let me try with the viewer here. Hopefully it's not going to crash this time. Okay, let me import the viewer. No, it crashed again. I don't know why this is not working.
The kernel was there at the beginning, so you probably need to rerun it.
Yeah. I did it, but you see now it's not defined. Let me kill this notebook and open it again. and see if that helps. I think what happens is I may have 2 instances. Yeah, I don't know. I guess it's Murphy's law. But let me try to open this again. Here. Okay. Yeah. I may try to do well. Okay. Let's see. Oh. Let's see if this works. I don't know why it's so slow now. Oh, it was open here. Okay. There is nothing else. Let's see here. Okay, it worked. Okay, now I can view. These are the regions. Okay, here it is. These are the same regions I just showed before. Using now this is MayaV. This package here is MayaV. It's a really nice package and can be integrated in Python. And then we can create the visualization for the actual solution. And this is the solution. And the nice thing about this is that it shows you not only the colors that we saw before, some a little bit different, but they are representing the same, but also the arrows show you the direction of the displacement. You see this corner here is moving in that direction, and this corner here is moving a little bit upwards and to the right. Right? No displacement here because the boundary condition was fixed displacements. And then a little bit of displacement here because of the boundary condition, right? And the body forces. But and the nice thing about doing it within the package is that they also have this kind of nice visualization options where it shows you a more physical representation of the solution. Oops. I think I might have used a very big number in the boundary condition, I think. And that's why, let me see again. Here, this number is supposed to be much smaller, I think. I probably don't need to do all that again, but I guess just in case. Now let's go to save the state. Okay, I wanna did I save it? I guess yeah. Okay, let's visualize it again. Okay, this is more like it, more like it's supposed to be. This is the boundary condition I'm applying. It's like if you saw it, it's a parabolic function. So you get that kind of shape because I'm forcing this behavior with the solution. This direction is because of the body forces, and I'm gonna show if I eliminate the body forces, you're not gonna see that, or if I eliminate that. So basically, what I have just done is taken what would happen if I had a piece of material and apply some boundary conditions, what the deformation would be. And as you see, this is a problem that, as I mentioned, if you wanted to write your own code to solve a problem like this, it would take you some time to do it, probably months. And not only that, you write your own code and probably it will work only for this physical problem. But with this package, you can solve any other problem that you want, even mixed problems, multi-physics problems. So that's basically what I wanted to show. So let's change a little bit the boundary conditions again. Here, for example, if I do, let me see the body forces. Okay, body forces is only in the vertical direction here. Let's eliminate body forces and see what happens. This is fine. Let me see exactly what I need to run. Okay, I need to run this because I have this, right? I just changed that, so I need to rerun this from this point on. And now let me, well, I really don't need this, but save the state. Now we can, of course, we can do better than this, right? This is just, okay. Well, this is not too nice. You see what you can do with the visualization. This is probably doesn't express too much what you want to see as this one. You see, it's more symmetric now, right? I eliminated the body function, the body force term, and the body force term basically what it's doing is pushing the whole system down a little bit. Now that I don't have that body force, now you see that this problem is very symmetric now. So there's not much difference between the bottom and the top, or no difference at all. And also you can try, say, probably we can change this function. For example, let's do a linear function. It's not going to be too much fun, but let's see what happens. And now let's go here. This is not what I was trying to do. Oh yeah, it's because I should have done this. I guess this is the reason. Okay, you see what is happening now. You have a straight line between this point and that point, and that's what the boundary condition is. It's not too much. It's not very interesting in this case. So let's do something more, even more interesting. What is it? Here. Do this. I don't even know what this is going on. What is the same. What it is going to look like. But I guess it's going to be something crazy. Yeah, something really crazy. It's too much. Probably I need to reduce that factor. So basically, this is creating some kind of very weird deformation. Probably can. Yeah, it's a crazy solution. It doesn't mean it's not correct. It's not very easy to understand what's going on there.
It's, I guess, a property of the material that you have as well.
Yeah, it's property of the material combined with the boundary conditions and the physics, right, and the equations that you're solving. But the point here is that you can solve basically whatever physics you want with whatever geometry. So in order to change the geometry, you will need to use probably a different meshing. You need to use your own gridding algorithm or package.